Hi all, welcome to new lecture of robotics and control. This is lecture 6 and today we are going to discuss forward kinematics of differential drive. So let's first describe what a differential drive car is. We will start with drawing a diagram of the differential drive car. We'll draw the base of the car and the wheels. So these wheels are motorized and they have separate motors. So each wheel can be run independent of the other. We'll now make a caster wheel to support the base of the robot, and we'll attach a coordinate frame to the base of the robot. The left wheel will run by phi L dot or angular velocity, and the right wheel will run with phi R dot. Let's say we want to move straight. So we'll set phi L dot and phi R dot to the same value. And if we want to turn, we'll set these values to be different. Now in a special case, if we want to turn in the same place, we'll set phi r dot to be negative of phi l dot. Now let's define the problem statement that we want to solve in this lecture. So given the angular speeds of the wheels, phi r dot and phi l dot, over a period of time, what will be the position and orientation of the robot? This is the problem statement we want to solve. So let's draw the position and orientation of the robots at two times. Let's draw it. Let's draw the initial position and orientation of the robot. Let the base of the wheel be separated from the center by a distance b, and the radius of the wheel be r. Let's draw the coordinate frame attached to the robot, which is coinciding with the base frame, and the coordinates of the center of the robot is given by xc naught and yc naught. Now let's draw the position and orientation of the robot at some time t. So you can see it is rotated from its initial orientation. So the base frame attached to it is also rotated. And it has also moved by certain distance. Then certain distance, and the angular velocities of each wheels are phi r dot and phi l dot. So now we want to compute in forward kinematics the position of point C on the robot with respect to the base frame. Please note xc naught and yc naught are the coordinates of point C on the robot with respect to the base frame. So point C is fixed with the robot. So when the robot moves, then the point C's coordinates with respect to base frame is the forward kinematics. So the way we will compute these positions and in future orientation is we'll compute the position by deriving the velocities of point C with respect to base frame, and then we will integrate integrate these values to get the positions finally. We will compute the velocities of point C with respect to base frame in a two-part process. In part 1, we'll assume only straight line motion of the robot, and in part 2, we'll assume only the rotatory motion. At the end, we'll add these two parts to get the final velocity values. So let's start with part 1, where we assume only the straight line motion. Let's draw the diagram of the robot. You can see it has been rotated by an angle theta and has moved to a new position. Its wheels are rotating by phi r dot and phi l dot respectively. Now let's draw a simplified diagram in which we can see where the wheels are touching the ground and where is the central point C. Now if we assume that one of the angular velocity of the right wheel is not 0, and for the left wheel it is 0, then uh, what will be the velocity or the distance covered in 1 second by the right wheel? It will be r phi r dot, where r is the radius of the wheel. You can see that point C is the midpoint of the line LR. So the velocity of point C will be r phi dot r divided by 2. This is the x coordinate of the velocities. Let's write the s coordinate of another case in which phi l dot is non-zero and phi r dot is 0. In that case, the velocity will be similar, but phi r dot will be replaced by phi l dot. The y coordinate of the velocities in both the cases will be 0 because the differential drive cannot move perpendicular to the wheel direction. If we add these two motions, that is both angular velocities of the wheels are non-zero, then we just add these two x coordinate velocities by superposition. So the velocity of x coordinate becomes r by 2 into phi r dot plus phi l dot, and velocity in y coordinate remains 0. So these are velocities in frame 1. What about the velocities in frame 0? From a previous lecture, we know that coordinates in frame 0 can be given by r1 naught multiplied by coordinates in frame 1, where c naught and c1 are coordinates in frame 0 and frame 1 respectively. If we differentiate this equation with respect to time, we get the following expression by the chain rule. The first expression, r1 naught into c dot 1, looks at translation motion, and the second expression looks at the rotational motion. Because we are only looking at straight line motion, we'll only use the first expression. So expanding the vectors, this is the expression, and if we expand the rotation matrix, we'll get the following expression. Now we'll replace the coordinates of velocities in frame 1 that we derived in a few moments ago, which is r by 2 phi l dot plus phi r dot and 0. If we multiply this matrix multiplication, we'll get the following expression. These are the velocities in frame 0 if we only consider the straight line motion. Let's box this equation. Now let us look at part 2. Here we assume only rotatory motion of the robot. Let's draw the diagram of the robot. Let's assume in the first case that the angular velocity of left wheel is 0 and angular velocity of right wheel is non-zero. We draw the simplified diagram like previously, and if this happens, the robot will rotate by some angle. Let theta dot be the angular velocity of robot, which we have to find. The distance between the two wheels is 2b. Then the velocity of the point r will be given by v1 equal to 2b into theta dot. Let's look at the cross section of the robot, and because there is no shipping at the feet, the velocity of the wheel at the bottom will be r into phi r dot, and these two velocities should be equal, and by this we get the expression for theta dot. Similarly, we can do an analysis for the opposite case in which phi l dot is non-zero and phi r dot is 0. In this case, theta dot will give the similar value r phi l dot upon 2b, but in negative direction, because negative sign is for because this will rotate the robot in clockwise direction. Previously, it was rotating it in clockwise counterclockwise direction. Now, if both the angular velocities of the wheels are non-zero, we can superpose, and the expression that we get from 3 and 4 equation is um, theta dot equals r by 2b into phi r dot minus phi l dot. Let's box this equation, and now let's try to combine these rotation and straight line motion. So as we said earlier, let's combine these straight line motions and rotatory motion to get the final results. So from the previous equations, star and dash, we will just copy those results here. So the x coordinate of point C with respect to base frame is half into r, that is radius of the wheel, into phi r dot plus phi l dot cos theta. Y coordinate of point C with respect to base is similar thing, but in the component is sine theta, and theta dot is half r divided by b into phi r dot minus phi l dot. If we try to simplify these expressions, we can let v equals half r phi r dot plus phi l dot, and theta dot equal to half r by b phi r dot minus phi l dot. We can convert these equations as follows. I think the above equation will be omega and theta dot can be written as omega. So these are the simplified expressions. We'll box them. Now we got the expression for velocities, but how do we calculate the expressions for the position and orientations? So we know the velocities, the expression for velocities at each instant, but how do we get the position and orientation? So there are two ways. One way is to find the analytical solutions of the differential equations that we derived previously, which are given as follows. Theta dot equals to omega. So these we had derived earlier. Either we find analytical solutions to this, which is a hard problem to solve. Other method is solve the above equation numerically. So we can solve these equations numerically. We'll use the second option. So let's solve the equations numerically, and the method that we use is Euler's method. In Euler's method, the x coordinate of c with respect to base frame at some instant ti plus 1 is given as x ti plus h times, so h is the time step, into velocity at ti and cos theta at ti. So x is positions at x, v and theta are position at ti, and x ti plus 1 is a position at ti plus 1. Similarly, we can write Euler equations for y coordinate of the position and also the theta coordinate of the orientation of the robot. Okay, so if we know the x, y, and theta velocities, angular velocities, we know v and implies that we know v and omega at instant ti, and these all are known to us if we know the angular velocities of wheels. Ti plus 1 is ti plus h is the time step. So if we know the initial conditions, that is initial position and orientation, and we also know the angular velocity of each wheel, then we can find the coordinates of the position and orientation of the robot at every instant. Now we can also use these Euler equations to animate the differential drive robot. So let's move to the Python environment to see how can we animate this in animate differential drive robot. Hi, welcome to the Python environment. Here I have a piece of code on differential drive forward kinematics. So in this code, we try to make an L and a shape of an L letter using the differential drive robot. I'll first run the code and show how it works, and then I'll try to explain how this code works. So let's try to run the code. So as you can see, the differential drive first moves in straight line, then again moves straight line in straight line. So this is how the code works. Let me now try to explain the code. The code is not very big. I'll also share the code in the description. So it's a 100-line code approximately, and most of the code is in animating, like 37 lines of code is in animating, and then there is Euler integration, and then there is a main piece of code. So here we first define the initial position and orientation of the robot. So it's at origin and it points downwards like minus 90 degree. We also define the h, the integration time step of the Euler equations, and then here is some commented code. We'll get back to this, why this is important. We'll discuss this also. But before that, we try to define three time steps, three time ranges. One for the straight line motion, then there is a turning motion, and then there is a straight line motion again. So each of the time range is of 1 second and with the time step of 0.1. Okay. Now, for us, the control variables are v and omega. Please note, in the theory we discussed that the control variables are actually the wheels omegas, right? So differential drive wheels angular velocity is our control, but here we have taken v and omega, that is the linear velocity of the robot and the angular velocity of the robot. Why is this the case? Uh, which is described here in the comment section. So this is the equation that we derived. So v and omega of the robots are a function of angular velocities of the wheels. Okay. You can write it in the matrix from like this, and if you inverse the matrix, you can get uh, um, always get the angular velocities of the wheel as a function of v and omega independently. So what does this tell us is, right, if we use v and omega as control variables, whatever v and omega we choose, we can always get a value for the angular velocities of the omega by this equation. We can always do that. So here we have what we have actually done is used robot velocity and angular velocity as the control inputs. Now we try to set the control inputs for each time range. For straight line motion, we have set the linear velocity to be 1 and the angular velocity to be 0. Then when we turn, we set the linear velocity to be 0 and the angular velocity to be uh, mm, pi by 2. And same thing again in the straight line motion. We set the linear velocity to be 1 and the angular velocity to be 0. Then we run a loop for where we do the Euler integration to Euler integration and save the all the position and orientations in the vector z. And later on, we use this vector t and z, which are the timestamps and the position at that time instance to animate the function. So the animation function is similar to what we have done previously. So I'll not explain this. I'll share the code. You can go through it. If you have any questions, you can ask me. Let's look at the Euler integration, how we are doing it. So Euler integration takes a range of time and initial condition and some control. So um, linear velocity is the first index of the control and the omega is the second index. And the um, this should be, I think, t. Um, yeah, this should be, I think, t. So it gives two time steps. Uh, okay, so um, you set the time step, then you set the initial position and orientations, and then you do the Euler integration. Basically, x1 equal to x naught plus x dot c into h, where x dot c is basically v into cos theta in the current time step at the current time, and we get the position x coordinate, y coordinate, and theta coordinates at the next time step, and we then return this value. So this is what Euler integration does, same as we saw in our theory. So let's run the code once again and see how it works. So it runs in the straight line, it rotates by 90 degree, and then it again runs in the straight line. So you can see here the omega is pi by 2 and it runs for 1 second. That the time span for turning is 1 second, basically 1 to 2 seconds. So it rotates by 90 degree. If we change it to, let's say, pi by 3, let's say, so it will not make an L. Now it will make some other angle. So let's see what it does. So it moves in the straight line, rotates by some angle, and then so it's not perfect L. We can also uh, change again the angular speed to 2 pi by 3, and let's see how it works. It moves in the straight line, rotates by, I think, 120 degree, and then again. So yeah, so you can play around with this code. I'll share the link to this code and along with it the GitHub link for where I add the notes and the codes for the previous lectures. You can have a look. So with this, I'll end the lecture and see you in the next lecture. Thanks.